So in my previous... Ooh, hello. So in my previous video where I talked about the magnetic angle resolver, I mentioned wanting to know the torque, the static torque applied to the system, and that is why I wanted to approach it as a servo. The reason I mentioned that a lot was because the video I'm making right now I've actually already made and was planning to upload before this. The lighting and the video quality was just so abysmal, I decided to reshoot the entire thing, but I didn't think of that while shooting the second video, so if it's a little out of whack, my apologies, but we're gonna go over it this time and I'll just link it in the previous video. So as I mentioned a couple times, I put a lot of effort into figuring out how much this was rotated and at what angle it was and what position all the different components were. And the reason I did that is because I really wanted to know how much torque, static torque specifically, was getting applied to the different components so that I could check how hard my gripper was gripping, how much effort it was to rotate the wrist, how much effort it's going to be to rotate different things and kind of detect issues early on, but also have interesting features such as where you just kind of push the robot in a position and it detects that it's being pushed and stops pushing back and just kind of goes with you. Or even just weird, funny functionality as the robot being able to tell you exactly how full a glass is just by weighing it. There's just a lot of different options that you can do with torque control. It's very nice to have it implemented as a debug feature also, because it's going to tell you a lot about how your gear trains are running, how everything is just kind of behaving. It has a lot of benefits, and so I really want to have it in my system. So yeah, I'm going to give you a quick rundown of what a servo is at the base level and why it's capable of giving you static torque, how torque and current actually relate to each other. And finally, a little demonstration where I actually take a standard servo. That's not it. And finally, a little demonstration where I take a standard servo and turn it into a surprisingly accurate kitchen scale. So yeah. So, servos 101. Now a servo is an example of a closed loop system. A closed loop system is just any system that tries to do something, knows what it actually did, and can then check if the thing it did is the thing it was supposed to do. So if you just have your standard DC motor, or really any motor, but we're gonna go with DC for now because that's what's usually in a servo. If you apply power to this, it's gonna start spinning, and you'll probably have some idea of what direction it's spinning in, but you really don't know how fast it's spinning, or really if it's spinning at all, if you're just looking at it from the view of a computer. So then usually what you have is some kind of output from the motor, an encoder, that tells you the position the shaft is in and how fast it's spinning as a result of it. Now if you want to bring the motor to a specific speed or a specific position, you're going to have some kind of signal that goes in here, and you're going to get some kind of output from your encoder, and you're going to have to compare those to each other. And the simplest way to do this is to basically just take your expected input, put that in your motor, and take your output and subtract it. So now you have your input and you have your output, and here you have the difference between the two. Now if your motor is doing exactly what you want it to do according to its input, then your output is the same as your input, and what happens here is 0. Clearly, if you want it to rotate continuously, that's not useful, but in terms of a servo, that means your servo is now not moving, which is what you want for a servo. So you give it a position, and then it'll move in some direction all the way until this difference between the input and the output is 0, and it stops moving. And then the more you push it out of that position, the more error you're reintroducing into the signal, and so the more power it's going to be drawing from your DC line. And that is, in a nutshell, what a servo is, and why specifically it only draws power as soon as you apply a force that pushes it out of its set point. So right now I have this servo hooked up directly through my power supply, because my power supply actually has a serial port so that I can hook into it with my Python scripts. So if I run this little script here, I get a live graph of how many milliamps are being fed into the servo. You see right now, it's not doing anything. It's just holding position, and so it's negligible. It's not even registering. However, as soon as I give it anything to do here, see, it takes more and more current as it tries to fight back, and then the amount of force I'm putting into this little lever right here directly corresponds to the amount of milliamps that are being supplied. As I mentioned before, the current through the motor is directly proportional to the torque being produced by the motor, and so as it's a servo and it only starts producing that torque as soon as it's out of its set point, you can actually get a very good idea of the static torque being applied to the lever just by looking at the current going through the system. And to prove this, I'm actually going to turn this servo into a kitchen scale by calibrating it to another kitchen scale. So I'm just going to turn this on. And I'm going to switch my script here real quick to just a simple little script that takes the readings and averages them out, so it's a little easier for me to write them down. The kitchen scale itself averages out already, so we don't have to do it on this side. So now what I'm going to do is I'm going to put weight on the scale, try and keep a constant weight, see what the current is doing, and just write that down. So for convenience, I just put down a couple of standard weights. I just put 0 grams, 25 grams, 50, 75, etc. And I'm going to try and put that level of pressure on here and just note how much current I'm drawing. So as you can see, there's a dead zone where it doesn't do anything. It looks to be about 22, 25 grams, so I'm just going to write that down as well. So now we're going to go for 50 grams. Let's say 132. Doesn't have to be super precise, it's just a quick demonstration. I'm going to go with 220 on this one. I did actually notice that I put this in the wrong cell last time, so I'm going to give that about 345. Let's say 450. Let's get that 480. So now it's just a measure of taking a simple linear regression through this. We know our offset. I'm just going to take these values. We actually want to know grams as a function of current, so it's going to be run over rise rather than rise over run. It's going to look something like this. So yeah, let's try these values out. So I'm just going to plug them in right here. So this is 0.417 times the milliamps, and then plus our offset, which is actually, I put a negative last time, my bad. But yeah, let's give this a try here. So you can see I now have a blue line as well, which corresponds to the y-axis on the right side, which is just grams. And we're going to see how well it does. As you can see, it is awfully close. So yeah, we just turned this little Tower Pro micro servo into a kitchen scale, basically. Clearly, this is only going to work with this stick of this specific length. This is exactly 10 centimeters from the pivot point. Because torque is Newton meters, so you got to divide it by your distance to get your newtons. Newtons then is basically just grams normalized to gravity. But as you can see, current versus torque, completely linear relation. And like I said, specifically for a servo, you can do it with a static torque rather than a continuously dynamic rotating torque, which is a lot more convenient for robotic grippers and arms and trying to figure out how hard your system's working or pushing against something. So yeah, I hope you found that interesting and it'll be useful to you, and I'll hope to see you next time. Bye!